All right. We've been talking about redox reactions, and what other types of reactions are there that you've encountered? A lot, but what we're going to do is we're just going to divide it into those three categories that I've been talking about. Redox, what were the other two categories we were talking about?
Acid, base, and metathesis.
Acid, base, and metathesis. All right, so let's just focus on redox reactions initially, and then we're going to look at the other types of reactions. For redox reactions, a lot of those redox reactions look pretty complicated. And in fact, a lot of them are pretty complicated. And so in Chem 4, you learned the technique. As far as redox reactions go, the first type of redox we're going to is the skeleton redox. The skeleton redox is you just mix it and see what happens. You have to mix it very carefully, otherwise something bad might happen, but mix and see what happens. So we can have certain things like this, CH3, CH2OH, which is, what's that called? Ethanol. Ethanol is a very common chemical. That's why I wanted you guys to memorize the name of this. So I think everybody has it memorized. If not, let's get into it. You should have this one memorized for sure. There are different ways we can write the formula for ethanol, but this is one way. This is called the condensed structural formula. The condensed structural formula versus this, the molecular formula, C2H6O. The problem with the molecular formula is there are things called isomers. So for example, if we had C2H6O, this could be something like this. Isomers have the same formula, so the composition is the same, but the structure is different. And so this is called dimethyl ether. Dimethyl ether and ethanol have the same formula. And so this is why we prefer things like this, the structural formula versus the molecular formula like this, because the molecular formula doesn't tell us what the compound is necessarily. This is an isomer. This is, let's do this as an aside. All right, what do you know about ethanol? Is it electron rich, electron poor? What do you know? What do you think? Ethanol. Electron poor? Well, what is the first thing you do in answering a question like that? Oxidation states. So just go ahead and do the oxidation states and you can see. We do the oxidation states for ethanol. This one comes out to -3, plus 1. This one comes out to, I'm visualizing the Lewis structure in my head. You probably want to just go ahead and do the Lewis structure. 2, 4, 5. This is -1, plus 1, -2, plus 1. Do those add up? Does it look right? So -3 plus 3 is 0, -1 plus 1 0, -1 plus 2 is +1, plus 2 minus 2 is 0. So it adds up. It's okay. What would you say, electron rich or electron poor or what? Maybe you haven't made the connection yet. The connection is this. Does ethanol burn? Is ethanol flammable? Are alcohols flammable, like rubbing alcohol or those? Yeah, alcohols are flammable. So if something burns, is it electron rich or electron poor? It's a fuel. You got to make this connection. I don't know how many times I repeated it, but lots. And you got to repeat it yourself, because if you don't repeat it yourself, you're not going to make that connection. So what is that connection? Are electron-rich species fuels or oxidizers? Fuels. And so does ethanol burn? Yeah, ethanol burns, therefore it's a fuel, therefore it's electron-rich. And this is what we call a hydrocarbon type group here. Hydrocarbons in general, hydrocarbons are highly flammable, like methane, ethane, propane. These are flammable. Butane. You know, it's just slightly oxidized because of the oxygen here. Mm-hmm.
Can you use like that? Can you explain again how, by looking at the oxidation states, you know they're electron rich or electron?
Looking at the carbon, the hydrogen and oxygens really don't tell us much, because hydrogen and oxygens just look like water, and water is not very flammable, is it? You know, although water can be oxidized with a powerful enough oxidizer. But here, I look at the carbons. Look at the carbons. What do you see? -3, -1. What's your first guess? Do you know the range? Can somebody just tell me the range of oxidation states for carbon? I don't know. You have to, you know, when it comes to the test, you can't ask me if it's right or wrong. Lots of people do. They come up to me, does this look right, or am I on the right track? But no, I can't tell you. You have to say it confidently. If you can't say it confidently, then you know, make sure by the time the test comes, you can. And so, what is the range of oxidation states for carbon? This is not a test question. Easily ask this on the test. Should be a simple question to answer. The range of oxidation states for carbon. -4 to +4. Good. -4 to +4. What side of the range is this on? Is it on the electron-rich side or electron-poor side? On the electron-rich side. The electron-rich, it's hydrocarbon. Hydrocarbon type. If this wasn't here, it's a hydrocarbon. Hydrocarbons burn? Yes, they do. They're electron-rich, right? And so, you know, the thing is, okay, making these connections is important. And so it's electron-rich, so we need some kind of oxidizer. Usually the oxidizer is oxygen, but we know what happens with oxygen. It's pretty straightforward. With oxygen, this burns to form CO2 and H2O. Let's pick a different oxidizer. Are there other oxidizers other than oxygen? Chlorine, right? Fluorine. What else? Well, we're going to start getting familiar with this chart, because on the periodic table, what's the strongest oxidizer on the periodic table? Fluorine. And we could see fluorine on this chart way over there in the back of the room. Let me turn this camera over. This is called the redox chart. Fluorine occurs here. Fluorine's the most powerful oxidizer, yet it's here. It doesn't matter, you know, where they put the strongest. The strongest could be on the bottom, the strongest could be at the top. It doesn't matter. They could flip this upside down. But we know, you know, no matter what orientation, we know where fluorine is. If we know where fluorine is, then we can figure out the rest, right? All you need to know is fluorine. A lot of people like to memorize things by looking at, okay, it gets weaker as you go down, but the problem is when they flip the chart upside down, then people run into trouble when they memorize that. And so what you do is you memorize 2 anchor points. The 2 anchor points are fluorine and, what's the other one? Lithium. Fluorine, on the one hand, is the most powerful oxidizer. On the other hand, lithium is the most powerful reducer. So no matter where the orientation, you can be in space where you don't know which way is up or which way is down. You can be in space and you can still determine which one's the strongest. because you don't care if it's higher or lower or whatever, you know where fluorine is. Fluorine's the most powerful, followed by what? This is something you do. The first time you're given a chart like this, what do you do? A lot of people ignore it because there's just too much data. Too much data, don't bother. But you shouldn't. You know, when you're given charts like this, you should just read through it. And you read through charts like this and you look for patterns. One of the patterns, okay, fluorine, chlorine, bromine, iodine, the halogens, right? The halogens are strong oxidizers, as you'd expect because they're just one electron short. Right? Oxygen, where's oxygen? Oxygen's here. Is oxygen a really powerful oxidizer? No, it's a mid-range oxidizer, right? Oxygen. There are many more powerful oxidizers. Do you see that? And so what we do is we get a chart like this, and some people ask me, should I memorize this chart? But I say, no, don't memorize it. But that doesn't mean ignore the chart. You know, some people say, okay, if it's not memorized, if I don't have to memorize it, I'm going to completely ignore it. But you know, when you're given a chart like this, you don't do that. Every scientist, what they do is they look for patterns, and they try to memorize the pattern, not the individual entries, if there is a pattern to the chart, right? And then by knowing the pattern, they can make predictions. Because the people who just memorize this, if something's not on the chart, they can't make any predictions. But the people who can memorize patterns, then if they're given something on the test that they've never seen before, they can place it because they know the pattern. Does that make sense? And so a lot of people, come up and complain, you never talked about that. We've never seen that. You know, but I know a lot of people get it right because they know, how to figure out the pattern. Okay, so here, well, how do you figure out the pattern? This can take some time. You know, you look at this, and you look at this, and you look at this. So you spend what you often do when you get a lot of data, you do something. Have you ever heard of data reduction? You know, data reduction, that's a fancy name for finding patterns. Sometimes you get 50, 60 pages worth of data and you're just pouring over that, and eventually you start looking for things that correlate. But anyway, here, this is a lot, and so what we're going to do is first we're just going to read it. Fluorine, what's that? H2O2. Another thing that people, one thing that always kind of surprises me, actually, this is portable, like this. One thing that always surprises me is that people don't even look at a chart like this, even during tests. Even during tests, they still get things like the charge on dichromate wrong. And they have this chart on the test. Or they get fluorine's charge, fluoride's charge, like -2. That's Chem 4. I give this on Chem 4 too, but some people still get fluoride as a -2 ion, stuff like that. Could be like a Chem 4 style mistake. But, it surprises me because a lot of ions are here, and yet people, I don't know, just miss it somehow. And so let's read them really quick. These should be pretty easy. What's this? Fluorine. What's this? H2O2. Hydrogen peroxide, MnO4 minus. Permanganate, Cl2 is chlorine, Cr2O7 2 minus. Dichromate, O2. Oh, actually O2. Why does O2? Look at O2's here and O2's here. What's the difference between these two O2s? Well, this O2 is a more powerful oxidizer. This is O2 plus 2H plus. This is kind of the same thing, O2 and H plus. And so do you see what the difference is between these two O2s? This one is much more reactive. This one's much less reactive. Why would one O2 be less reactive than the other? Both of these are diatomic. O2, O2.
The amount of O2 is the.
This is not the amount. This is just the ratio. 1/2 to 2 ratio versus a 1-to-2 ratio. These don't say I have a 1/2 mole. It just says they'll react in a ratio. I could have any amount I want, so I could have a ton of this and ounces of that. Depends on something. The other thing is you need to read the captions. A lot of people don't read the captions. This is for 1 molar and 1 atmosphere. And so this would be O2 at 1 atmosphere, O2 at 1 atmosphere. So we have 2 O2s at 1 atmosphere. One is much more reactive than the other. Why? This is a pattern you probably can figure out yourself or see. Why is it? The product, exactly. This one forms water, whereas this one forms hydrogen peroxide. Hydrogen peroxide is a heck of a lot less stable, so this reaction is going to be much less favorable. This reaction is going to be much more favorable. And so that means O2 is actually a pretty strong oxidizer here, stronger than bromine. What's this? This is nitrate, but there's H+. Actually, let's take a look. There's H+ here, H+ here, H+ here. What's going on with all this H+? Do you see that? What's going on with all that H+? It's not hydrogen bonding. It has to do with something else. This is acid. H+ is acid. So why are we adding acid in these?
To free their protons that are formed when the acid breaks down.
Yeah. Protons will be formed when the acid breaks down. So, but it doesn't really break down. It just breaks apart into ions. So. But there's another reason, this one doesn't have any H+. This one doesn't have any H+. No H+ here, no H+, no H+, no H+, no H+, no H+. Do you see a pattern with the H+ and the no H+? Can you see it? What do all the ones with H+ have in common? Well, these are all, a lot of these are aqueous. Yeah, you're right, those are all aqueous. But here, this is not aqueous, this is liquid. It would be pure bromine liquid. And so being aqueous is not it. It's related, but it's not it. They have water as a product, good. They all have water, and they're all oxygen containing. Do you see oxygen, oxygen? Oxygen. And so one of the products here that's going to be stable is water. If you look at the oxidation states of H+, it doesn't change. H+ goes from +1 to +1. So H+ doesn't participate in taking or losing any electrons. It's just there to help form the stable product, water. Okay. Anyway, we look, and so we could try let's try another one. Another oxidizer rather than oxygen. We know we can burn ethanol, but I want to try something else. What I want to try is, I want to just try to mix it with permanganate and H+, like on that thing. And so what I do is I do this carefully because I know that I could get quite a big flame with oxygen, so I mix these two carefully and then see what forms, And what forms in this case is under these conditions, the conditions change depending on how you react it, but under these conditions I got some CO2, and the permanganate goes from a deep purple, which is characteristic to a very light faint pink, which is characteristic of manganese 2. So the permanganate changed from a deep purple color to a light pink color, indicating that we went to manganese 2. This is what we call a skeleton reaction, because we just mix these together and saw what happens. We didn't really predict what's going to happen. Just kind of mix it and see, carefully, of course. Because this is a potentially dangerous reaction. And so, let's just say carefully react, or allow to react. But is this balanced? No. And so you guys have balanced these skeleton reactions before, right? So we're just going to do one quick review, and then we're going to move on to newer stuff. What's the first step in balancing a skeleton redox? And so this is given. And so reaction did occur. And these were the major products. You know, reaction occurs, that means a driving force is present. You know, we talked about driving forces earlier. We're going from less stable to more stable stuff. And so, what do we have to do? Well, given that, then we must balance it, right? And so let's talk about balancing skeleton redox reactions. Balancing skeleton redox. Uh-huh.
Don't you have to separate by half?
Yeah,
reaction?
right. So we separate into two half reactions. Separate it for me. The ethanol goes to CO2, right? Well, as we know, when we burn ethanol, we can form CO2. Actually, complete combustion of ethanol shouldn't lead to, or complete oxidation of ethanol should lead to, what? CO2. Could we get CO3, CO4, CO5, CO6? No, we know it's going to go to CO2. And so what if I didn't tell you what the product was? I just said we're going to oxidize the ethanol using permanganate, which is the very powerful oxidizer. If we're oxidizing the ethanol, what do you think it's going to be oxidized to? What would you take a guess at? CO2. With an oxygen-containing species, as long as there's oxygen present. And the other one is permanganate goes to Mn2+. Right? And so let's quickly do this. First, we balance all elements other than carbon and hydrogen. No, not carbon, oxygen and hydrogen, excuse me. And so we have 2 carbons here, 1 carbon here, so we need to multiply this by a coefficient of 2. Then we balance what? Hydrogen or oxygen next? Oxygens. We have 1 oxygen here. We have 2 times 2 is 4 oxygens here. And so how do we balance? Do I multiply this by 4? No, I can't. I have to do what? Plus, I need 3 oxygens, so I'm going to do plus what? 3 H2Os, okay? Then I'm going to balance the hydrogens next. So that's 6 plus 9, 10, 12. 12 hydrogens on the left, and I have 0 hydrogens on the right. And so how do I balance out the hydrogens? I add 12 H pluses, and then I balance the charge. Looking at the charge, this is neutral, 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 and 12 plus. And so we have 0 on the left plus 12 on the right, and I balance it by adding electrons. So I need plus 12 electrons here. And so that should lead to what we call a balanced, what? CH3, CH2OH plus 3H2O yields 2 CO2s plus 12H plus 12 electrons. This should lead to what we call a balanced. Yes.
How come you're leaving it at H plus?
Hmm?
How come you're leaving it at H plus?
How come I'm leaving it at H plus? Why?
Aren't you supposed to turn it to H3O plus?
Oh, okay. How come I'm leaving it at H plus? H3O plus is technically, it's more correct. So H3O plus is better, but it takes too much time. H plus is a shorthand representation for H3O plus. And so H plus doesn't really exist in solution. We use H plus to represent H3O plus and higher, you know, but we use H plus all the time because it just saves time, saves space.
Because my Chem 4 teacher was like, that way is wrong if we should do it.
Your Chem 4 teacher's correct. You know, it's wrong to do it, right? It's wrong to do it, but it's just an abbreviation that we use, abbreviated method. Otherwise, every single table, you know, would take up so much more space. And so technically you're right. In Chem 1B, we're going to be much more particular about sticking with H3O+, but in Chem 1A, we aren't. In Chem 1A, we're just going to use H+. Now, H plus AQ doesn't exist because this is a tiny proton. Tiny protons are too reactive. And so look at all these. These are all in terms of H+. And the same thing over here. These are all in terms of H+. Yes, it's wrong, and I'm glad you know it's wrong, but it's right because what we're going to do is we know what the real situation is. The real situation is that H plus just represents H3O plus. If I wanted to change this, I could change it easily. You know, what I do is I just add 12 waters over here, add 12 waters over here, and then we could have it plus 15 waters and plus 12 H3O pluses. Then it maintains the balance. But, you know, that just takes up more space, and it's not necessary to do. But I'll leave it up to you. If you want to continue doing H3O plus, do it. Okay? Just make sure it's balanced. We can always double check the balance here, like the carbon balance. We've got to make sure, but I didn't finish. What is that called? Is that called a balanced reaction? Is that a balanced reaction? Well, let's see. 2 carbons, 5, 6 hydrogens, plus 6 is 12 hydrogens, 12 hydrogens, 4 oxygens, 4 oxygens. Oh, the atoms are balanced. Is that a balanced reaction? No. No. It's not. We don't call it a reaction. What do we call this? No, we don't call it balanced redox. We call it a balanced half reaction. Why do we call it a balanced half reaction?
Because the electrons are
Right, electrons. That's it. The free electrons don't exist either. We aren't going to have free electrons. We're just using the free electrons to keep track of the exchange here. So for example, if you wanted to go grab a bottle of 12 electrons, 12 moles of electrons off the shelf, are you going to be able to do that? Yes or no? No. Hey, these 12 moles of electrons are products. So what I'm going to do is I'm just going to let those 12 electrons go into a jar and close the jar, and then I'll just have some electrons. 12 moles worth of electrons. Yes? No. No, and so this is called a half reaction because we need the other half. The electrons just can't sit there. Something had to take those electrons. You know, they just don't get spit out. And what took the electrons? There. Well, we need the other half reaction. So let's go ahead and balance this one. And so here, the manganeses are balanced. So we have manganese is check. Then oxygens, we have 4 oxygens here, 0 oxygens here. So that means we need plus 4 H2Os. And then let's balance out the hydrogens. We have 0 hydrogens here, 8 hydrogens here. So we'll have plus 8 H plus. And let's balance out the charge. So plus 8 minus 1 is plus 7. Plus 2 over here. And so we have to balance the charge by adding negative electrons. And so we'll need 5 electrons over here. And so I'm going to just write this permanganate plus 8H plus 5 electrons yields Mn2 plus 4 H2O liquid. So here's what took the electrons. But as you recall, here we have 12 electrons lost, but only 5 electrons gained. That can't happen, because what's going to happen is if we add these up, we're going to have net electrons left over, and we can't have free electrons left over sitting in solution. And so we need to do something with this. What do we need to do? This is the other half. And so 2 half reactions will add up to a whole reaction. But we have to do something in order to get these 2 to add up properly. What is that? We have to balance the electrons. We have to balance the electrons lost and electrons gained. And so here we lose 12, we gain 5. So how can I balance that? I'll just cross multiply. It's probably easy to do. And so here I'm just going to multiply everything by 5. Here I'm going to multiply everything by 12. And so 5 times 12 is going to give you 60 electrons lost, and then 12 times 5 is 60 electrons consumed. You know, something like that. Maybe you could find a smaller factor, but this should work. Okay, so we just added up. Well, the thing is, when we have a balanced half reaction, we can double check these. The way we double check these is we make sure the atoms are balanced, and we have to make sure the charge balance is. So over here, there's neutral, 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 plus 12, minus 12. So it's 0 on the left, 0 on the right. Same thing here, we have to make sure the charge balance is plus 7, plus 2, plus 2, plus 2, and plus 2. And so the charge is balanced, the atoms balanced, these half reactions are balanced. Okay, the net redox reaction has to be balanced too. And so we go with 5 ethanols plus 15 H2O plus 12 permanganates plus 12 times 8, is that 16? 96? 96 H plus 60 electrons. Okay, that's everything on the left. This is going to produce everything on the right. So I'll write that down here since I ran out of space. So 5 times 2 is 10 CO2s plus 60 H plus 60 electrons plus 12 Mn2 plus 4 times 12 is 48 H2O liquids. Just leave out the liquid. We'll do the states later. All right, so the most important thing is that the electrons consumed is equal to the electrons produced, so they cancel each other out. We can also simplify in other ways, because when we look at this, we have 60 H pluses as product, 96 H pluses as reactant. So let's get rid of 60 of those. That leaves me with 36 H pluses here. What else can we simplify? 15 H2Os, let's get rid of those. Take off 15 from here, which would give me 33 H2Os. Okay, can we simplify anywhere else? No, it doesn't look like it. And so what we end up with is 5 CH3 CH2OH plus 12 permanganates yields 10 CO2 plus 12 Mn2 plus 33 H2O. All right, let's double check to see if this is balanced. And so 5 times 2 is 10 carbons. 10 carbons. This is 6 times 5 is 30 hydrogens. I must have made some kind of mistake here. You see, I must have made a mistake because hydrogens aren't balancing. This is 5, 6 times 5 is 30. I got 66 hydrogens. 30 and 66, I made a mistake somewhere. Right? It's not balancing. And so I gotta figure out where my mistake is. Uh-huh.
You got the 36.
Yeah, okay, I forgot this 36H plus here. Here, that's it. And so let's see if this balances now. 36H pluses. So 5 times 6 is 30. 30 plus 36 is 66. 66 hydrogens, 66 hydrogens. That works. How many oxygens? That's 5 plus 12 times 4 is 48. 48 and 5 is 53. This is 20. 20 and 33 is 53. So oxygens are balanced. 12 manganese, 12 manganese. So the atoms are balanced. The atoms must be balanced, along with what else must be balanced? What else has to be balanced? The charge. So what's the net charge on the left? Hmm? The net charge on the left is, what's the charge on ethanol? 0. So 5 times 0 is 0. What's the charge on permanganate? -1. So 12 times -1 is -12. The charge on hydrogen, +1 times 36 is +36. So -12 plus 36 gives us 24. +24. Over here, this is 0, so 10 times 0 is 0. This is +2. 12 times +2 is 24. And this is 0, 33 times 0 is 0. So +24, +24, the charges are balanced. So this is it. All right, so this is pretty much what you did in Chem 4, right? You might have had to do something else. You know, this is for acidic or neutral solutions. You might have had to convert it to basic solutions. Did you have to do that by adding hydroxide to both sides? Yeah. In order to convert this to basic, in basic solution we can't have strong acid exist, so we'd add 36 hydroxides on the left. 36H plus 36 hydroxides yields 36 waters. But that screws up our balance, because if we add 36 hydroxides on the left, we better add to the right 36 hydroxides. And so we gotta add it both to the left and to the right, otherwise our balance is just all screwed up. Okay, but this is not in basic solution. How do you know if it's in basic solution? Somebody will tell you. If it's not specified, then you assume it's acidic or neutral. Okay. Is that clear? Since I didn't specify, we're going to assume this is fine. Okay. In basic, you would have just converted all the H plus into waters. All right, so this is kind of Chem 4-ish level. What we're going to do is Chem 1A level now. Chem 1A level, we're going to add a couple of things to this. One, you know, the methanol, what do we call that? The methanol, is that the reducer or is that the oxidizer? This is the reducer. The reducer gives up the electrons. So the reducer is electron rich. And so we say everything here, the ethanol in the water, this is going to be our RA. RA stands for reducing agent. What's the permanganate doing? The permanganate's taking the electrons. The reducing agent is producing the electrons. Do you see this is electron rich because electrons are a product of this. Permanganate is electron rich or electron poor? Permanganate. Permanganate is electron poor. You see it? Why? It's the oxide?
It's the oxidizer.
It's the oxidizer? Yes. Permanganate's the oxidizer. It's electron poor. But why is it electron poor? I know it's because it's an oxidizer. Oxidizer in general, electron poor, but you know. The charge on what?
Manganese.
Yeah, the charge on manganese is what?
+7.
+7. +7 makes it A powerful oxidizer or moderate oxidizer or weak oxidizer? A powerful oxidizer. You see it's the third most powerful one on the chart. You see that? That chart's not complete, of course. It wouldn't be number 3 on other charts. You know, there's an expanded version of that chart in your book called in Appendix D. But permanganate's the oxidizer. And we need the H+. Why do we need the H+, even though the H+ doesn't do anything? Why do we need that H+? What does the H+ do in a lot of these? You know, if the H+ wasn't there, is that okay? Let's say if the H+ wasn't here, would permanganate still be as powerful as it normally is, or does it really need that H+? It doesn't really seem like it does much, or does it? Can I just, if the H+ wasn't there, would permanganate be as reactive? This is a question. This is a question that after some time, I know that you just heard about it today, you know, this stuff up here. But this is a question after some time you could probably answer. And if the H+ wasn't there, then we wouldn't have what form on the right side? H2O. And if we didn't have H2O, we'd have something less stable. And do you know the stability of the product? Does the stability of a product make a difference in reactivity? Yes or no? Does the stability of the product make a difference in reactivity? Sorry, I was trying to get the chart there. Let's see if I can get the chart. Yes or no? Give me one example, specific example, where the stability of the product made a big difference in reactivity. One specific example. The O2s, right? O2s, although both of those O2s had H+, but the difference was in the product. Now, if we don't have water forming, we're going to have a much less stable product, meaning the reactivity is going to go way down. And so this H+ is kind of critical. This H2O is not so critical here, but we'll just throw it in because in this particular reaction, that's what we have. And so do you see the reducing agent produces electron, the oxidizing agents consume electrons. This is redox. Redox, we also give another name for these reactions. The other name we give these reactions are electron transfer. Electrons are being transferred from the reducing agent to the oxidizing agent. This is why we want electron-rich species as the reducing agent, electron-poor species as the oxidizing agent, because we want the electrons to be transferred. Right? Now, here's our oxidizing agent here. Now we have to think of these as, or imagine these as being reversible reactions, you know, because oftentimes when we think about chemical reactions, we think of competition between the products and the reactants. And so let's look at this as being kind of a reversible reaction here. If this reaction went backwards, then what's CO2 and H+ doing? CO2 and H+ is doing what? CO2 and H+ is taking electrons. If something takes electrons, what does that make it? An oxidizer or reducer? If we go backwards here, CO2 plus 12 H+ plus 12 electrons yields those, if going backwards. So that means that these species are the oxidizers. And so what we call this is, we call these the OA. OA stands for oxidizing agent. What is the electron spore species there? What is electron pore species there? What's the oxidation state on carbon? +4. Okay, carbon dioxide and H+. Look on the chart there. Do we see carbon dioxide and H+ on our chart? No, it doesn't occur on the chart. So does that mean, if it doesn't occur on the chart, that means maybe it's not an oxidizer. Maybe I should erase that. No, and obviously you know that chart's very small, right? And that chart is missing thousands and thousands of oxidizers. Maybe more than that, hundreds of thousands or millions of oxidizers probably. So a lot of stuff doesn't occur on the chart, but we know from our own factual knowledge, from our own basic experience, that carbon dioxide is a weak, moderate, or strong oxidizer. Weak, right? We know that. And so we could easily place it. It's going to be weak. How weak? Extremely weak. You know, they have carbon dioxide fire extinguishers. Have you ever heard fan the flames of the fire? When you fan the flames of a fire, what are you doing? You know, or blowing on the fire. Have you ever done that? Fan the flames of a fire? And then the flames grow bigger? What are you doing? Giving more oxygen, because oxygen is a oxidizer, so you're providing more oxidizer. Well, what's CO2? CO2 is an oxidizer, right? +4. But what's a CO2 fire extinguisher doing? It's extinguishing the fire. It's not fanning the flame, so that tells you that CO2 is not a very good oxidizer for wood, paper, fires. For maybe oil, but oil you probably wouldn't want to use. I don't know. Maybe you could use it. For metal fires, would you use CO2? No, you would not use CO2 on metal fires. Why? Yes, because metals are strong reducers. And CO2's, even though it's extremely weak, is strong enough to oxidize a metal because metals are easy to oxidize. So you never use CO2 on a metal fire, right? Because it's an oxidizer. And so we have a seesaw relationship here. The seesaw relationship is like this. Do you guys remember the conjugates? What does conjugate mean? Conjugate, not in math, in chemistry. Conjugate pair. Tell me what a conjugate pair is in chemistry.
Like opposites.
Okay, let me be more specific. What is a conjugate acid-base pair?
Like if it's an acid in the opposite side,
Mm-hmm.
and then it will have a conjugate base in the reactions. Like
Yeah.
after
Right. The conjugate acid-base pairs. And so, for example, HCl would be the acid. Its conjugate base would be, well, H plus is not the base, but Cl minus. So this is what we call a conjugate pair. The acid and base, these form a conjugate pair. What do you know about the strengths of conjugate pairs? Boy, this should be easy, the conjugate stuff. I think. Is it? Or you don't remember at all? Because if you don't remember this is one of the major topics in Chem 4. Conjugates. If one side is strong, the other side is weak. That's the conjugate relationship. And so here, this is strong. This means this is weak. In redox, we have the same thing, except we're not going from the acid to the base, we're going from the oxidizer to the reducer, or vice versa. And so redox is exactly the same relationship, because if this is a strong acid, HCl is, then the proton's lost easily. If the proton's lost easily, that means chloride has an extremely weak attraction for protons, as it must. The conjugate relationship happens here. You know, if ethanol is a strong reducer, then that must mean that CO2's got to be a weak oxidizer, because if ethanol is a strong reducer, then it gives up its electrons easily. That means CO2 is not going to strongly take these electrons and go backwards, reverse the reaction. Do you see that? And so if one side's strong, the other side's got to be weak. And the same thing over here. If permanganate in H+ is a strong oxidizer, that must mean what is weak, and what specifically is weak? Well, there's a conjugate relationship. Maybe I'm jumping too far ahead. This is the reducing agent here. And so what we do is we know this reaction occurs. If this reaction occurs, there's a driving force present. In redox chemistry, the driving force is this. The driving force in redox is we go from stronger, not strong. It doesn't have to be strong. It just has to be stronger. So we go from stronger to weaker. What? Stronger OA to weaker OA. Stronger RA to weaker RA. And so the way I write that is SOA to WOA, SRA to WRA. Like that. So the extra step we could do in this skeleton redox is we can get some strengths of oxidizers and reducers. And so over here we have ethanol. This is our reducing agent. And over here we have permanganate and H+. This is our oxidizing agent. Over here, what's our oxidizing agent? Well, over here the CO2 is our oxidizing agent. And the manganese and water, this is our reducing agent. And so what this tells us is this reaction occurs, so there must be a driving force. So we're going from stronger to weaker. And so in other words, as far as reducing agents go, ethanol is a better reducing agent than manganese 2+ in water. Permanganate, an acid, is a stronger oxidizer than CO2. This one we could have figured. All right. So that's a little bit harder than what Chem 4, right? Because we've got to look at the oxidizing agents and reducing agents. And the easiest place to look for oxidizing agents and reducing agents are in the half reactions. Because if you look down here, it's hard to see what takes electrons, what gives up electrons. But in the half reactions, it's very clear to see because the electrons are shown. And you can see who produces the electrons and who consumes, you know, permanganate consumed, ethanol produced. Likewise, we can go backwards. If we go backwards, we see that CO2 and acid consumed and manganese and ion and water produced. So the half reaction is the key here to seeing this easily. Okay, also in Chem 1A, you're going to be kicked up a notch too. And so let's see. Actually, let me back up one step. Or let's see. All right. This skeleton, the next series of reactions we're going to encounter are ones where we actually have to predict the products. In a skeleton, did we have to predict the products? Did we have to predict the products in the skeleton? No, because the major products were given. Okay, for this next series, you're going to have to predict the products. So the first type we're going to just look at is element plus element. You know, so if I have let's do sodium solid plus chlorine gas, what do you predict will form there? NaCl. Exactly. And then we'll need 2 sodiums. Sodium chloride, NaCl solid. That's it. Hydrogen gas plus oxygen gas. What do you predict? Water. And so we could do 1/2 O2 here, etc. Although maybe we'll do one more. Sodium solid plus sulfur solid. We can predict will form here. Sodium sulfide, what's the formula? S. 2 sodium. All these have the same kind of driving force. You know, we're going from stronger. You know how powerful sodium is a reducer, right? Chlorine's a powerful oxidizer. Our sodium ions, what would be the oxidizer and reducer in the reverse direction? So a lot of these are just, this is our Ra, this is our OA, right? Looking at sodium chloride, we have sodium ions and chloride ions locked into the lattice. So of those two, going backwards, which one's the oxidizer, which one's the reducer? Yes. Oxidizer. And so this is very clear. What's a more powerful oxidizing agent? Chlorine gas or sodium ions? Chlorine gas, much more powerful. Do we need the chart to tell us this? Not at all. These are pretty straightforward. In fact, in Chem 4, you didn't even write the driving force, did you? You didn't even bother, because why? Somebody already figured it out for you that you didn't have to bother. You know, the problem is in Chem 4, they try to limit it so everything works out. You know, but what happens if they give you something that doesn't necessarily work? Well, they wouldn't. They wouldn't because, but in Chem 1A, they might. You know? And so we have to be a little bit more prepared for this. But these are going to work, you know, quite nicely. B, we have single replacement. You remember single replacement? Can somebody tell me General form of single replacement?
Like in the variables or
Just in letters, whatever.
A plus bx.
A plus bx yields, yeah, ax plus b or b plus ax, whatever you want. It doesn't matter the order. Correct? All right, in Chem 4, in Chem 4, they're careful in choosing the problem. They want to make sure the problem works. If they give you a pattern like this, would they throw a failure into the pattern? In other words, is this a law, or is this some kind of rule? The difference between a rule and a law, a law you would expect to hold consistently, right? But a rule has plenty of exceptions, lots of exceptions to the rule. Is that a law or is that a rule, that form? So anytime we get a pattern that fits that, it's always going to react like this. Well, let's give you one example here. Let's give you silver solid plus HCl. What will this give you? Silver solid plus HClAQ. Well, follow the pattern. AX, silver chloride, plus B, hydrogen. But hydrogen is not monatomic. Hydrogen is diatomic. So we need to balance this. So I'll need 2 of these, 2 of these, and one of those. H2 gas. Silver chloride, do you know, is that soluble in water or insoluble in water? Boy. Well, actually, you have time. You have time. You have to have the solubility rules memorized by exam 2. Okay.
exam 1, what's going to be on it?
Chapters 1 through 4.
Okay, that's solubility rules, aren't you?
No, I introduced solubility rules early so that it gives you a head start on memorization. That's all. Because I take a long time to memorize things. It's fine. And so I would have started long ago because I'm slow in memorizing. And I forget things easily. And so I need that constant. The other option, this is what I used to do too, is, worst case scenario, you still don't have it memorized. Well, do this. Right before you get the test, get it in your short-term memory. And right when the test is handed out, write it down. That way you can forget it. That's better than failing that part of the test. I used to do that a lot. But it led to a lot of stress because more and more things piled up that I had to get into my short-term memory, and it just didn't work. Up to a point, yeah. Anyway, getting back to this, is there a driving force for this? What was the driving force for single replacement reactions? The single replacement, was it gas formation? Was that a driving force for single replacement reactions? Yes or no? Yes or no? Gas formation. We're forming hydrogen gas here. So is gas formation a driving force for single replacement reactions? Yeah, the answer is no. The activity series is the driving force for single replacement reactions. So we look at the activity series. Which one is more stable? They do it by element. Which one is a more stable element, silver or hydrogen? Yeah, if you were to fill up your trunk with silver or hydrogen, which one would be more stable? Silver. So silver is what we call less active. Hydrogen is more active, less stable. And so we see that we're going from less active to more active element. And therefore, is this a driving force? No. Because the driving force is going from more active to less active. We want to go from less stable, more active, to more stable, less active. This is the opposite. And so this is what we call NR. What does NR stand for? No reaction. We shouldn't get any product here because there's no driving force. But, hey, did you memorize this reaction as one of the exceptions of single replacement? Did you memorize any exceptions? You know why? You didn't have to, because the Chem 4 instructor carefully selected all the reactions so that you wouldn't have to deal with any exceptions. Otherwise, it's too much to memorize. How many exceptions are there? A lot. A lot of exceptions. If there are a lot of exceptions to the rule, then does it work so well? So why learn it? Why learn the rule if there are a lot of exceptions? Well, you know, once you see the pattern and the exceptions, then you can quickly figure them out. Like one of the patterns in the exception is that single replacement works with mineral. Oops, this is right. This is right. This is not an exception. This is right. Because this is what we call a mineral acid. If, on the other hand, I tried this, I took two silver solids and reacted with, oops, I'm not going to use, well, actually, since I already know the balance, two nitric acids to produce two silver chlorides, oops, silver nitrates, sorry, and hydrogen gas. So that first reaction is actually right. We expect no reaction, but the second reaction looks exactly the same, doesn't it? It looks exactly the same to me. It's just another strong acid, HCl, HNO3. Both of them are strong acids, right? But this is wrong. This does not form. And this is wrong. There is reaction. Reaction occurs. Reaction occurs. And so, you know, after you do a lot of these, then you'll see, oh, a lot of the exceptions just follow a simple pattern. And we can see that pattern. So, you know, single replacement's quick and easy, right? And so one of the patterns that you probably didn't learn is that it works for mineral acids, but it does not work for, what's this called? Nitric acid is called a what acid? It works for mineral acids like HCl, acetic acid, HBr, HI, etc. But it does not work for this type of acid, and this type of acid is called a when are you gonna get it down? Because the test is coming up next week. So did anybody review that? Actually, let's see if it's in your notes. If it's not in your notes, then yeah, you aren't going to get it anyway. But it's at least in your notes. At least you might study it right before the test, get it in your short-term memory. But you know, too much stuff in your short-term memory is going to overload it. So do you have do you have something in your notes where we wrote down this? HClO4, HNO3. Is there anything?
Doesn't it break up in the two?
I'm sorry? It breaks up?
Doesn't it continue to break down?
Yeah. Yeah. Breaks down. It breaks down into what though? H plus and ClO4 minus? It was at the same time I talked about this stuff. NH, did I talk about this stuff? NH4 ClO4. Did we talk about that? Okay. Well, I'll talk about it now. There. What's special about NH4ClO4? It's got a weird name, yeah. Can you name it? Ammonium perchlorate, that's the name of that stuff. Ammonium perchlorate. What's special about ammonium perchlorate? Ammonium perchlorate is a very special chemical. And I want to show you something here. Something that happened in Nevada. Actually, is this the, I don't know if this is the one I want. No, that's not the one I want. Let me see. This is the one I want, I think. Oh, is that the one? I wonder what happened to the audio. Every time somebody messes with the audio on this thing, it just doesn't go. But this is a ammonium perchlorate factory in Nevada. And it's much more dramatic, if you could hear it too. Enormous. I mean, you can't see the scale of that. That's a gigantic plant there. Enormous explosion. And these guys on the video are pretty funny too. if you could hear the audio, but the audio's screwed up. You should check it out on YouTube. Ammonium perchlorate is a very dangerous chemical. Why? Somebody tell me why ammonium perchlorate is such a dangerous chemical? Did you see? Look at this explosion. Horrendous.
Is it because that like the chlorate or perchlorate is a very powerful oxidizer, and the ammonium is its fuel? So
Yeah.
they're both in the same substance.
They're both in the same substance, the ammonium and perchlorate. So you have the fuel and the oxidizer in the same compound. Obviously, it's going to be very dangerous. That's what happened. It unfortunately reacted at the plant there and destroyed the plant. And I forgot how many people were killed in that explosion, but yeah, it was pretty bad. But anyway, this is a little bit better, right? Because this doesn't have the fuel, but it does have the. It doesn't have the fuel, but it does have the oxidizer. So we call these oxidizing acids because, you know, although H+, you know, H+ is an oxidizer too. Because if you look at the chart over here, on the redox chart, you'll find H+. But where's H+ in terms of oxidizing strength? Well, if we go over to the chart here, you know, H+ is here. We wouldn't call it, you know, we call it very strong oxide. No. H+ is a mid-range oxidizer. But perchlorate, where would actually perchlorate's not on here. Perchlorate's not on this chart, but you should be able to figure out where to position it based on its oxidation state. What is the oxidation state? Chlorine and perchlorate. The oxidation state of chlorine and perchlorate is plus 7. How many valence electrons does chlorine have? 7. Do you think chlorine's going to be happy losing all 7 of its valence electrons? How many plus 7 cations have you seen? What's the highest charged cation you've ever encountered? Plus 3. What is your feeling about a plus 7? Happy? No, it's not happy. It's not happy. You know, plus 7 charge, the reason it's plus so high is because it's stabilized by the oxygen. It's not a true plus 7, like a monatomic. You know, the oxygens help stabilize that. But still, it's in a very high oxidation state, meaning perchlorate's pretty nasty stuff. And so, this is what we call an oxidizing acid. What about nitric acid? How about nitrate? Well, nitrate does occur on that chart, and we already saw it, but what would you think, just based on its oxidation state? How many valence electrons does nitrogen have normally? 5. Nitrogen, what's the oxidation state of nitrogen and nitric acid? Plus 5. Do you see a huge difference between these two acids? You know, I see a huge difference between these two acids in their way they react. The problem is in Chem 4 you probably don't. In Chem 4 you probably think of these two as being the same. They're both strong acids, right? But no, they're quite a bit different. Okay? It's true they are both strong acids, so they'll react with bases, but this is not an acid-base reaction. This is a redox reaction. Redox reactions, we treat these two differently. And so this is what we call an oxidizing acid. This is what we call a mineral acid. Major difference there. Take a look at this ammonium perchlorate explosion, and you can see, you know, how violent some of these redox reactions can potentially be. Extremely violent. And so therefore, when I mix this with the oxidizing mineral acid, mix it together, right? Oxidizing acid, I got to be careful. In fact, I probably wouldn't want to do this. Here, you know, HCl and silver, I'll do this on the bench here. Do it on the bench, no big deal. Oxidizing acid, I don't want to do it in the bench. You know where I want to do it? I want to do it inside the hood. And I want to do it carefully. Because I don't know what kind of nasty stuff is going to form, unless I've already predicted it. And so what we're going to do is we're going to predict what's going to happen here. And so let's try to predict what's going to happen. Well, we need some way to predict it, because single replacement fails in this case. Single replacement fails. Single replacement also fails in other types of redox unless you memorize a pattern. How many single replacement patterns do you have memorized? Do you have the x2 plus ax pattern memorized? No, x2, not x2. x2 plus ay pattern. Do you have the x2 plus ay pattern memorized? The x2 plus ay yields ax plus y2 pattern. Do you have that one memorized? If you don't have this one memorized, then you can't do this type of single replacement, can you? You know, some Chem 4 instructors make them memorize this. I do. I made my students memorize this second pattern too, because this is a very common reaction. It's a very common reaction because what happens if you try to do this? Cl2 plus NaBr produces what? Does it produce the ax plus b, or does it produce the 2ax plus y2? Which one does this fit? This looks like an a plus bx. Is it an a plus? No, it's not an a plus bx because this is an x2 plus ay pattern. Do you have it memorized? Yes or no? No, then the situation is all you can do is a very limited number of redox reactions right now. Very limited. That very limited, we can't leave it that limited because it's too limited, you know, the Chem 4. And so what we have to do is we have to expand this. And so what I say is just, you know, single replacement's great. You can do them very fast. So when speed's an issue, this is great. But you have to know the patterns. And then you have to know the patterns upon patterns, where it works, where it doesn't, like oxidizing acid versus mineral acid. But I'm going to give you something that takes a little bit longer, but you don't have to worry about exceptions because there aren't, as long as you can find. You know, there aren't many because redox, I should say there's always potential exceptions because depending on the conditions you run the reaction, you know, the temperature, the pressure, these kinds of things, it can change things. Like, for example, we predicted ethanol should be oxidized to CO2, but why wasn't oxidized to carbon monoxide or carbon? Well, it could have been. It could have been under certain conditions, right? You know, not only that, ethanol under very mild oxidizing conditions gets oxidized to acetic acid. Have you ever heard of wine turning into vinegar? You know, I was out in Joshua Tree, and I was at the the dollar store, one of those, and I saw Santa Barbara wine, $1 bottle. Wow, because I'm from Santa Barbara, so I saw Santa Barbara wine for $1 a bottle. I'm going to buy it, you know, over 21, of course. So I went and bought it, then took it back to the campground and tasted it, and it was vinegar. Oh my God, that was a waste of $1. And so, you know, under mild oxidizing conditions, ethanol doesn't get oxidized to CO2. Ethanol gets oxidized to vinegar, you know, basically. Well, anyway, we'll stop here, and we're going to talk about more general approach.